everyone. My name is Luowei Shao from China Special Equipment Inspection and Research Institute. Today, I would like to share my research work about the research on acoustic emission monitoring technology for corrosion of Q345R low alloy steel and 347H stainless steel in high temperature melting salt environment. Firstly, I will choose our background and motivation behind monitoring the melting salt corrosion, and then I will introduce the experimental preparation of the monitoring system. Then I will give the relationship between the AE signals and the corrosion process, demonstrate the damage identification of melting salt corrosion. Finally, I will give the concluding remark. As we know, the melting salt thermal storage technology is originated from the in the 1960s in the United States. China since introduced this technology and constructed numerous plants. And the high temperature melting salt technology is in high demand for applying, including melting salt reactors, concentrated solar power plants, and the flexibility retrofits for thermal power plants. The safety and the service life of these systems are critically constrained by a key bottleneck, namely the long-term corrosivity of high-temperature melted salts towards structural material, including low alloy steels and austenitic stainless steel. Melting salt storage tank operates under harsh conditions. The material of the melting salt tank with a lower temperature of 219 centigrade is Q345R. With a higher temperature of 565 centigrades, 347H. The later lies within the sensitization range. It is a large structure. It is a large structure with numerous complex welds and designed for 25 to 30 years. It is hard to apply inspection in service. So we will do the research about the monitoring in-service monitoring. So the monitoring damage during service of the melting salt tank is a major challenge because the acoustic emission technology can offer an in-situ, real-time, and continuous damage monitoring. But there are also some challenges. The first one lies in extracting the signals in the very complex environment, noise. And the second one is how to assess the damage of the material in the melting salt environments. It is very hard. And we construct a melting salt corrosion AE monitoring system, just like this. And this is a design drawing. And we use waveguide load to influence the the temperature is not very high for the AE sensors. The unpressed and repressed corrosion specimens were fixed to the waveguide structure using bolts and nuts, respectively. The material of the high temperature waveguide rod must be consistent with that of the molten salt storage tank and to prevent the galvanic corrosion. The required waveguide rod length was calculated using the heat conduction equation that accounts for convective heat transfer. When we apply the corrosion test, molten salt corrosion test, the corrosion mass loss of 347H under different stress increased rapidly initially and then slowly with time, with the overall trend approximately parabolic curve. The corrosion rate of 347H under different pre-stress initially increased rapidly, then decreased quickly, followed by a slow decline, reaching a peak around 250 hours. During the initial stage, the unstable oxide film accelerates corrosion. The slowing increase in corrosion mass loss and the decrease in corrosion rates after 250 hours can be attributed to Wagner's oxidation theory. As shown in Figure 1 and Figure 3, the data for corrosion mass loss versus cumulative energy were fitted using different models. For the 0 megapascal and 120 megapascal pre-stress conditions, linear and nonlinear equations were applied respectively, yielding coefficients of the determination of 0.957 and 0.978. In contrast, linear equations were used for both the 0 megapascal and 80 megapascal conditions, resulting in R square values of 0.972 and 0.947 respectively. All models indicate a good fit and positive correlation between the variables. As shown in Figure 2 and Figure 4, fitting with a nonlinear equation and long coordinate yielded high coefficients and of determination superior to linear fitting, showing a negative correlations. And there are three stages in this test. In this results, in stage 1, spectrum is unimodal. The peak frequency is about 115 kilohertz. But in the stage 2, the spectrum is bimodal, and there are two peaks. There are another new mechanism in this stage. And in the stage 3, the spectrum is turned to unimodal again, and the peak frequency is about 61 kilohertz. So the mechanism of the corrosion is different. Both duration and rise time exhibit three-phase evolution patterns, revealing the dynamics of the corrosion process. The application of 120 megapascal pre-stress significantly increased single duration and rise time, indicating a more intense corrosion reaction. The temporal evolution patterns of cumulative hits and cumulative energy will consist across different sample durations, namely 20 seconds, 60 seconds, and 180 seconds. Consist three-stage growth pattern was observed for both cumulative hits and energy rapidly increase and slowly grows and further deceleration for 792 to 1032 hours. A uniform three-stage corrosion process was identified for both Q345R at 400 centigrade and 347H stainless steel at 565 centigrade. The critical difference lies in the transition speed. At 347H stainless steel transitions through the severe and decelerated corrosion stage more rapidly than Q345R, entering the low corrosion stage earlier. This indicates that the stainless steel forms a protective oxide layer more quickly. 347H possess a superior ability to form a stable protective oxide layer more quickly. When we check the morphology, when we check the morphology of the corroded specimen surface, AE signals in Q345R are generated by the strain energy released during the rupture and the spoiling of the corrosion products over time. Pre-stressed intensify Q345R corrosion, leading to great and consequently a higher rate of AE signals than in stress-free specimens. And when we check the relationship between the AE signals and the melted salt corrosion, the energy release rate of the unstressed specimen remained at a low level during the 0 to 480 hours period. At this stage, a relatively complete protective oxide film may form on the material surface, resulting in slow corrosion progression and no strong AE source. At 72 hours and 168 hours, corrosion products, ferrite oxides and sodium ferrite oxides were generated respectively. Cumulative energy can be used. Cumulative energy can be used to characterize the changes in corrosion products of 347H stainless steel. So classification of AE signals in melted salt corrosion stages based on AE characteristic parameters. The melted salt corrosion process of Q345R steel at 400 centigrade was divided into three typical stages. A total of 1,500 burst type signals were equally selected from these stages, with pre-trigger data retained and no overlap between signals. Subsequently, FFT and STFT based frequency domain database was constructed. The proposed new method achieved over 90% accuracy in automatically identify AE signals all three corrosion stages. The method maintained high identification accuracy under different stress conditions, indicating its robust and adaptable performance. Now, its concluding remarks. Robust conclusion was correlation was established between the AE parameters and the three stages for both two materials in molten salt, confirming AE's efficacy for in-situ mobility. Applied stress is significantly intensify corrosion activities and AE signals generation. With stressed specimens exhibiting great damage, higher cumulative hits and energy compared to stress-free counterpart. A spurious representation-based method successfully identified the corrosion stage with over 90% accuracy, demonstrating a novel data-driven approach to quantitative damage assessment in molten salt environments. A developed AE monitoring system and damage identification method provide a viable foundation for the integrated management of critical components like molten salt storage tanks in concentrated solar power project, molten solar reactor systems, and flexibility retrofitting for thermal power plants. Thank you for your attention.